Okay, there we go. Everybody's coming back in. Awesome. Gonna get my document camera set back up here. Yep, there we go. That was our old meeting session number. Okay. Let me get my chat pulled up. Hopefully this is kind of, everybody's doing okay with all of this loveliness. I'm going to try and make sure I don't have anybody that I'm losing over here in any of my stuff. I've been trying to watch all of my email accounts and all of that good kind of stuff all day. It's been great fun. Okay, so we're going to do section 3.5, and this one is going to be rational functions. Okay, and this is one I actually just got done doing this one with one of my dual credit classes. So I'm pretty good with all of this. So I'm going to go ahead and switch to our document camera. Flip to where it's long ways for me. Okay, and I'll bring this out like that. Okay, so rational functions. Now, rational functions are going to be in the form P of x over Q of x, and Q of x cannot equal 0. Okay, and guys, we kind of already played with these before back when we did like composition and combining functions. We talked about, hey, these are ones where, you know, we got to talk about like domain problems. We cannot let our denominators equal 0. It's just not allowed. Okay, so if we want to talk about doing some domain stuff, and guys, please let me know if you cannot read one of these marker colors. To me, some of this stuff looks really faded, or if some of the colors come out better, okay? And I'll try and figure out, you know, which colors come up the best for this stuff. I'm kind of switching around for some things. So, okay, so if we're going to look at something like this, and we want to talk about the domain, okay, then what we're going to do is we're going to take that denominator and we're going to say it cannot be 0. And then we're going to solve. There's our domain. Okay, x can't be 5. Now, and guys, it truly is that simple. Okay, so please do not like make this into some complicated thing that it's not designed to be. Okay, now we're going to look at another one. Okay, because sometimes these things have more than one value that's going to be off limits. So we've got x squared minus 25. Okay, and again, I'm going to take x squared minus 25 cannot equal 0. We're going to move that 25 over to the other side. Now, when we bring in, because I'm going to need to do square root to get rid of the squared, okay, so we're going to take square root on both sides. Since we brought in the square root, we have to bring in a plus minus, okay? So x cannot be plus or minus 5. Now, sometimes they will make you, like, separate those, okay? Bring that down just a little bit, okay? Sometimes they'll make you write them separately. I'm okay with it being in the plus minus form. That, to me, doesn't bother me, okay? So let's take a look at one more. Sorry, something big is going by my house. Okay, so we've got x squared plus 25. Now, slightly different. The last one was minus 25. This one's plus 25. So now, kind of the same step process. Now, guys, here's our concern. Okay, I now have x squared cannot equal negative 25. If I go to take square root on both sides, I'm now trying to take the square root of a negative number. That's complex. That goes to imaginary. It's going to bring in the I things, okay? that means the only problems that we have are not in our regular world, okay? They are over in the complex world, which means all real numbers, again, sometimes abbreviated like that, okay, is our domain, okay? So, if you have, so again, the only reason this came up is because when I go to take square root of a negative, that's going to give me imaginary stuff. Now, the next thing that we're going to talk about is called approaches, okay? Now then, I'm going to put in a graph picture here, okay? Oh, I hear my puppy dogs. They are not happy right now, okay? Okay, so this is a graph shape, okay? And so when we talk about approaches, okay, the notation here, and I'm going to explain what all this means. Okay, because that doesn't really read. Okay, so it says as X, this arrow means the word approaches. The number 3, now this negative, guys, there's 2 ways that I can come towards 3. I can come this way, or I can kind of come from this other direction, okay? Now then, this one indicates which way I'm coming from. So this says I'm coming from the negative numbers, so I'm going to come this way. And then, guys, the second part of this just says, what is my graph picture doing? If I come along and I'm coming over here, all of a sudden this thing starts to go, whoop, and it's headed down. So it says the graph is approaches or goes to negative infinity. It's headed downwards, okay? Now, we can also do as X approaches 3, and if I want to come from the positive side of stuff, then we just put a little positive plus up there, okay? And let's talk about what that one does. So if I get on the graph over here, and I start coming towards 3, my graph starts heading up, way, way high. So that means that thing is headed up towards infinity, okay? Now, there are 2 other things that we can talk about the graph doing, and that's what's happening when it goes out here towards the edges, either direction, okay? Now, for these, we don't have to indicate a direction. So if we say if X is headed towards negative infinity, y'all, there's only one way to head towards negative infinity, and that's that way. Now, I have not drawn this graph super great, okay? But this, what's happening with this graph, and let me trail this in a little bit better, okay? What's happening with this graph is it's going to come up and get really, really close to our x-axis, but it doesn't ever actually hit it, okay? So this is getting really, really close to the number 0, okay? And then we also have the same thing happening on the other side. So as x heads out towards infinity, our answer values are getting really, really close to 0 when that happens, okay? So you're really just talking about what the graph does. Now, one of the things that now comes up is what the crap is going on. Like, why is there this gap in my graph this way, and why is there a gap in my graph this way, okay? Now then, one of the things, okay, that as a high school teacher, okay, is one of my first years, or my first couple of years teaching, especially my first year teaching, I had a group of seniors that I had to teach this type of graph to, okay? And what happened was I was having to talk about what this was, like the technical thing. And guys, coming from, my math background, I had, been in, I had a degree, I had 2 degrees in mathematics. This was just like everyday language for me. It didn't matter. But my high schoolers, okay, it was not. So I go in and I start talking about what that graph thing is, what that gap is, okay, and what's going on. And my students go, oh, Miss Comstock. Actually, it was Miss Hood at that time, but you can't say that word. And I'm thinking, what word did I say? And they're like, you said a bad word. And I'm like, what bad word did I say? Okay. And I was like, so, and they started getting super giggly. Like every time I would say this word, they'd be like, and they would start snickering. And the class would go off the rails. Okay. Like done. Okay, like here is 10 minutes of my time trying to get them back on track for where they were. Okay, so I was like, you know what, this ain't gonna work. So I had to come up with a way to talk about what this thing was. Okay, without using the fancy technical term for it. And I'll say it here in a minute, so you'll kind of know why my students said, what they said. Okay. But I also needed my kids to remember it. Okay. And what it did. And I have students that will come back. I will see them. Okay. Like I had them, and now, they took a little bit of time off, and now they're coming back to college, and they're like, oh, I'll take Miss Comstock. And when I tell them, when I say and tell the story, like, oh, I remember what that's about. And I'm like, okay, good. Okay, even though it's been several years, you remember what it's about. Okay, and so what I told my kids is, I have a younger sister. She's 4 years younger than me, which is great. It's wonderful. We were never on the same campus at the same time, except for elementary school, except we fought a lot. Okay, so what would happen is we would go on family vacations, and my mom would try and do the good stuff. She'd do like books on tape. Y'all, I can only ever listen to the end of those, like, this concludes side A, cassette 1. Please turn to side B to repeat the story. Beep. I can only listen to that for so long. Okay. My mom would get the little magnetic car games. That was great until the magnet pieces fell to the floor. Okay. And then you would get ratcheted into the seat. Okay. By trying to reach down because that seatbelt would lock up. And so, we would be like, those pieces would, end up at the floor. My mom, in her wonderful wisdom, would allow me and my sister to bring one toy from home. We were Barbie children. We loved Barbie. It's great. So we would bring Barbie. And inevitably, at some point in time, my mother, okay, and I know my mother's face, okay, I'm going to demonstrate my mother's face because I know what would happen. She would be sitting in the passenger seat of the front seat, and me and my sister would be arguing in the back seat, and all of a sudden she would just go, okay, and that hand would come back between the seats, and that meant handed over. Okay, she wasn't going to say anything. Okay, it just meant handed over, because then the next set of lines was, girls, Barbie's been a lot of things in her life. She's been a doctor. She's been a lawyer. She's been a teacher, and she's fixing to be a pilot because she's going out this car at 70 miles an hour. Windows coming down. We're like, no! So we hand over now. So Barbie now is in the front floorboard. She is POW MIA. We are not getting her back for the rest of the trip. Don't send G.I. Joe after her. It's over. Okay, so now whoever's Barbie got taken up first, it was then the goal of the other one of us to get the other Barbie taken out, and it would happen. Okay, we both. Now, at some point in time, usually about 30 minutes into the trip, those of y'all with kids, you know what I'm talking about. Okay, we're done. Both Barbies are in the front floorboard. We're not listening to whatever is my mother's playing on the radio or whatever. We're not doing any of that. Okay, and my sister will lean over, okay, and go, I'm not touching you. I'm not touching you. I'm not. Now, I was fine with this game. I was a good big sister. I would have appeased her for a little bit. Okay. But then I got tired of the game. And apparently my response was incorrect. Now, I learned very quickly. I was a daddy's girl. I always rode behind my dad. And then I got smart and I rode behind my mom. Okay? Because what was going to happen is, apparently my response was incorrect, although I don't get it. Okay? But she would do, I'm not touching you. I'm not touching you. I'm not touching you. I would lean, ooh, you touch me, smack. I touch you back. Apparently that's the wrong response. Okay, but it was smack and tuck, okay? And I would automatically try and tuck into that back corner of the car, because the next thing I knew, my mother's hand was going to come flying out of the front seat. Now, I have yet to figure it out. My mother's arms are either made out of Stretch Armstrong stuff, okay? Because there is no way it is physically, humanly possible for her to have found me in that back seat, but she did, okay? So it's either Stretch Armstrong or she's got like Go-Go Gadget arms. I don't know which, okay? But it happens. Now, the point is, and my kids always got a great, laugh out of the story or whatever else. And I said, the whole point of the story is the I'm not touching you game part, okay? Because what happens with our graph picture, okay, and usually what happens is we use kind of a dashed line to indicate this. Our graphs get really, really close to these lines, but they never actually touch them, okay? So now, the word for this, and I've also been told that I say this word slightly wrong, I add an extra A sound in the middle, is asymptote. Okay, so again, having giggly seniors, they always try to tell me that I said, a nasty word or a bad word, but it's not. Now, the question is, how do I find these? Okay, so, and we do have a couple of different types of asymptotes, and you'll see me abbreviate them, okay? So, the first one is vertical asymptotes. Okay, vertical asymptotes happen when the denominator has problems. Okay, so this happens when the denominator has problems. So if we look at something like this, okay. Now, first off, I'm going to worry about the domain. Okay, so we're going to have x squared cannot equal 1. We're going to bring in that square root. So x cannot equal plus and minus 1. Now, that's our domain. Okay, for your vertical asymptotes, you have to separate them because they are at 2 separate locations. So anything that is a domain problem, okay, which is going to be when the denominator goes to 0, okay, any of those values, the x equals, okay, and this is a vertical line format from back when we did lines, okay, these are the 2 spots. So if we were looking at a graph picture, I would have 1 here and 1 there, okay. Now, the next type is horizontal. Okay, so we're going to get rid of all of this. Yep. So the next one is horizontal. Now, they're going to make some big hoopla to do about this, and they bring up this whole big, especially if you looked in the PowerPoint. It's god-awful, okay? So here's what you need to remember. Bobbio, Botno, Ratco, okay? Bobbio, Botno, Ratco. Now, what this means is we're going to be looking at the powers, okay? And we're going to look at the highest power, okay? If the highest power between the top and the bottom, if it's bigger on the bottom, okay, then it's going to be y equals 0. If the bigger power is on the top, which is bot, then there is no horizontal asymptote. And if they match, okay, then it is the ratio of coefficients. Okay, so Ratco. Now, I'm going to show you a couple of examples of this so that you can see what's going on when I'm talking about Bobbio, Botno, Ratco. Okay. So, first example, we've got 9x squared over 3x squared plus 1. The degree, guys, is that biggest power. So the degree on the top is 2. The degree in the denominator is also 2. This matches. So this is Ratco. When we do Ratco, we are coming right in front of those biggest powered terms. So here it is. So it's going to be y equals 9 over 3, which is 3. Okay, so graph picture wise, I would go up here to 3, and there would be my line. Okay. Now, another example. Okay, is I've got 9x cubed over 3x squared plus 1. So our degree on the top is 3. The degree on the bottom is 2. Okay, and again, it's only the biggest power that we're looking at here. Okay, this is bigger on top. Okay, so there is no horizontal asymptote. Okay. Hopefully everybody's good with that one. Okay, now I'm going to do one more. I'm going to bring this down to here. Okay, so now the degree on the top for this one is 1. Okay, because guys, the x is there. Remember that the power is 1 if they don't put 1. Our degree on the bottom is 2. We are now bigger on the bottom. So that is Bob. So automatically have one at y equals 0. Now, graphically, what's going to happen there is it's going to sit right along that x-axis for when that happens, okay? So now then, there is one other type of asymptote that can come up, okay? And this is a very special one, okay, when it comes up. And this is a slant asymptote. Sometimes I call them oblique asymptotes. I call them slant asymptotes, okay? Now, these happen, okay, first off, you have to be in a Botno situation, okay? So it has to be a Botno situation, but specifically, the degree on top is 1 more than the degree on the bottom, okay? So for example, this would be something like x squared over x plus 1. I mean, I could have 3x plus 7, okay, over x plus 1. Our degree on the top is 2. Our degree on the bottom is 1, okay? This is a bigger on the top, okay? So it's bot, but it's also 2 over 1. Guys, if this was a 3, it is still a Botno, but it does not have a slant because 3 is not exactly 1 more than the degree on the bottom. Now, in order to find them, you are going to have to do division. Now, with something like this, you could do synthetic division because that is an x plus or minus a number, okay, on the bottom. If it is something like x cubed over x squared, okay, again, we are in Botno, but it is 1 higher. Guys, this one you would have to do with long division, okay, just so that you're aware of that. So, taking a look at an example for one of these slant asymptotes, okay, went the wrong way with my camera. There we go. So we've got 2x squared minus 5x plus 7 over x minus 2. And again, if we look at the degree on the top, it's a 2. The degree on the bottom is a 1. So we are in bigger on top, so Botno, but we are exactly 1 higher. Now, again, with this being an x plus or minus thing, we can do synthetic division. Again, opposite into the box because we have the x minus here. I've got 2, negative 5, and 7. Skip and draw. 2, 4, negative 1. 3, negative 2, and 5. Okay, I'll move this down a little bit. Now, keep in mind, that was x squared, so this is x, number, and remainder, okay? The only part of this that we need for our slant asymptote is this part. So we would have the line y equals 2x minus 1, okay? So if we were going to go have to graph that, I'm trying to pull my stuff over here just real quick, okay? Again, I would have vertical ones someplace in here, okay? But I would start down here at negative 1. I would go up 2 over 1, okay? Just creating that line that we've done with slopes before. And so I'd have a slant asymptote that looked like that, okay? They are exactly that they are a slanted asymptote, okay? Now, when you are getting ready to graph, okay, rational functions, my order that I do differs from the book's order, okay? Because I feel, I want to know personally, what stuff is kind of off limits for me. Like, don't use these numbers. Let me know that first before I get into the stuff. So my order is vertical asymptotes. Then I want to find horizontal asymptotes, okay? And up underneath that would be slant if it's going to happen, okay? The third thing is I want my y-intercept. And in order to do that, you're going to plug in 0, okay? Next, I want my x-intercepts. And this is, you take the top and you set it equal to 0, okay? Now, when you create, when you put your asymptotes on a graph, okay, when you put those in, it creates zones, okay? So kind of you got the stuff on this side of the asymptote and you've got the stuff on that side of the asymptote. If there's more than one asymptote, then you're gonna have more than like the two zones, okay? You need to plot at least 1 point in each zone, okay? Now, I'm gonna put symmetry down here. The book puts symmetry a little bit higher up, okay? I don't. Because a lot of our rational graphs do not have symmetry, and so therefore it's not going to exist, okay? So I don't rank it real highly, and then we put all this stuff together. So we're going to look at graphing one of these. Oh, and I'll mention that in the graphing. Let me make myself a note. Okay, I'm making myself a note to tell you guys something here in just a second, okay? So we're going to graph 3x minus 3 over x minus 2, okay? So first thing I said is we're going to find our vertical asymptotes, okay? So vertical asymptote is first. We're going to set x minus 2, and if you're just looking for the vertical asymptote, you're not having to do the domain, you can leave off the not equals to. The not equals to is for the domain. The equals to does your asymptotes, okay? So we're going to have one at x equals 2. So I'm going to get, I'm trying to get some graph space on here. Okay. And I'm going to try and do this in a couple of different colors just so that you can see the different portions. Okay, so there is my line at x equals 2. Okay, horizontal asymptote, come back up here. The degree on the top is 1, okay, because my biggest power up here is 1. The degree on the bottom is also 1. Okay, so I'm going to go find, that is a Ratco. If my video froze, it's going to come up. It'll catch back up here in just a second, okay? So I'm going to take the ratio of my coefficients. So this is going to be y equals 3 over 1, which is 3. Okay, so 1, 2, 3. Okay, so it's going to come up here in just a second. Okay, then I had my y-intercept, which is we're going to plug in 0. So I've got 3 times 0 minus 3 over 0 minus 2. That is going to be negative 3 over negative 2, which is going to be 1.5, positive 1.5. I'll move this down just a little bit so you can see. Okay, so my y-intercept is here. Okay, x-intercept is I take the top and I set it equal to 0. Okay, so this is here. Okay, and guys, y'all already seen the graph shaping that we saw before. Okay, these are kind of these little branchy pieces. Okay, so because I've got those two things there, okay, I'm going to pull that. Now, I do need to figure out what's going on. Move this over here on this side. Okay, so what I'm going to do, and I don't need a whole lot of points. This was at 1, 2, so I'm going to figure out what's happening at 3. If we plug in 3, we've got 3 times 3 is 9, minus 3 is 6, over 3 minus 2 is 1, so that is the number 6. So I've got this dot that's going to be up here. If I extend this asymptote up just a little bit, okay, that means this graph piece is here. Okay, so hopefully everybody, I'll move this down just a little so you can see what I did. This is, I just plugged it. Now, you can always plug in more points, okay? You can plug in like the number 4, you can plug in the number 5, anything that's over here on this side so that you understand what's going on, okay? Now, that is the end of what I had in the PowerPoint. I did want to talk about one quick thing that can happen, okay? And remember, I am going to put all this up. These videos will go up on YouTube. One of the things that I wanted to talk about is, and guys, I'm just going to make something up here, okay? Okay, so let's say that you've got something that has 2 asymptotes, 2 vertical asymptotes, and I'll put in, let's say, a horizontal one that went right here across the x-axis. Now, one of the things that's going to happen is you are going to need to get points in this zone, and this zone. Okay, now what happens here is the horizontal asymptote, when we talk about stays off of it, that is for the edges of your graph, the way out here at the edges, okay? Because I have seen graphs where we have points that are up here, okay? So it looks like this graph goes this way. Then we get points that are like here, here. We actually hit the x-axis, okay? Which kind of makes, you know, no sense because it's got a horizontal asymptote. This thing actually arches through here, and then there's like another couple of points that are like down here, and so this piece goes like this, okay? So keep in mind that if you get, you know, double or more than that vertical asymptotes, okay, you may have a graph that actually crosses over in the middle of the graph, and that is okay, okay? I've also seen these graphs though, okay, where they don't do that and they just kind of come up and down this way, okay, and they kind of stay off. So I just wanted you to be aware of the fact that you can have graphs that do this, where they truly do stay off of all of the asymptotes, but you may also encounter a graph where it does actually do this crossover point right here in the middle, and that's okay too, okay? So that is the end of section 3.5. I hope you guys have a great evening. The next one of these sessions that I'm looking to do is probably going to be on Monday, and I may have to do one Monday, Wednesday, Friday of next week, so that one on Monday is not super long. So, and we may have to do it again kind of in parts and pieces. So, but I will put an announcement up in Canvas for what time all of that is going to be at. I'm going to try and do it closer to class time. So kind of going back to that 5 o'clock time. So hope you guys have a good rest of your evening, and I will talk to you guys later.